Hi, I'm Antonio Sala, and in this video we are going to discuss the concept of LMI set or SDP-representable set and put forward a first bunch of examples. Subsequent videos will discuss additional examples and some geometric or optimization problems that can be done with them. LMI stands for linear matrix inequalities, SDP, semi-definite programming. They are kind of the same thing depending on which book you read. So, an LMI is a big symmetric matrix whose elements are linear function of some decision variables x. For instance, this big matrix down here. And the inequality comes from the fact that we will assert the condition of this big matrix being positive semi-definite, all its eigenvalues being non-negative. So an LMI set will be the set of feasible values so that this matrix is positive semi-definite. In abstract terms, this LMI will be the same as this sum of the decision variable x1 times a given matrix with the coefficients of the elements in here, symmetric of course, plus x2 a2 plus x3 a3 plus a0 for the affine terms such as this one, this constant thing, etc. So these are two equivalent representations. Doing optimization on this kind of sets is called semi-definite programming. So the feasible values of this inequality define a set that, which shape does that set have? Well, we'll see some examples in a couple of minutes, but first, two properties of this kind of sets. First, these sets are convex. Indeed, imagine that I have XA, 1, 2, 3, let's say three components set in 3D space that belongs to this LMI set I called capital S. Then if I have another point in the set, call it XB, also components 1, 2, and 3. Then if a matrix is positive semi-definite, so it is any combination of such matrices with positive coefficients. It's easy to understand that fact because if for any psi transpose M1 psi is non-negative and psi transpose M2 psi is also non-negative, then of course lambda times this plus 1 minus lambda times this thing will be non-negative, and hence the matrix lambda m1 plus 1 minus lambda m2 will be positive semi-definite. Then, if the blue matrix is positive semi-definite and the green matrix is as well, lambda times the blue matrix plus 1 minus lambda times the green matrix will be positive semi-definite, so it ends up proving that the convex combination or the line between XA and XB also belongs to the LMI set capital S. So LMI sets, whatever they are convex shapes. And in fact, they are also the so-called semialgebraic sets, which are the sets defined as the set of points in which some polynomials, the set of polynomials is positive, and which polynomials in particular are we referring to? Well, forget about the red B subindex, but a matrix is positive semi-definite if and only if all the principal minors are greater or equal than 0, so the determinant of this 1 by 1 this is this thing, this first degree polynomial, the determinant of this piece of the matrix is the thing, and that must be also a positive thing. This will be a degree 2 polynomial in a generic case. And the determinant of the full matrix must be also non-negative, so this will be a degree 3 polynomial, possibly, unless I have a lot of zero terms or whatever. So the set of the 3D space in which these three polynomials are positive is the LMI set. And as we said a minute ago, it's a strange set, but whatever the thing it is, it's a convex shape. So these are the convex and semi-algebraic sets defined as LMI sets, which I summarize like this. There are another LMI sets in more dimensions, so that the set in X is the projection of that set on the X coordinates. These are the so-called lifted LMI sets, and discussion and examples of them will be deferred for next video. Now we will just consider this kind of sets and put forward some examples using YALMIP and SEDUMI in MATLAB. And if you want more information on LMI sets, you can look for courses of Didier and Rion, or search in the web for LMI representable or SDP, semi-definite programming representable sets, and you will find stuff there. But okay, let us start with the examples, because otherwise we don't really understand what we are doing. So we will load our toolboxes into the MATLAB path. So depending on how you installed them, maybe your commands will be different, but okay, in my case, YALMIP and SEDUMI will be on my MATLAB path. And well, the simplest LMI sets are polyhedra or polygons in 2D, because, well, a linear inequality scalar, it's a 1 times 1 linear matrix inequality. So the polygon AX less or equal than B, with this A and this B, is defined by 4 inequalities, one for each side or face of the polygon. And of course, scalar linear inequalities, we can do optimization on them with, let's say, linear programming, if I optimize x1 plus x2. But of course, semi-definite programming is more general than linear programming. So if I check a SDP solver such as SEDUMI, and I put this linear matrix inequality constraints, because these are 4 1 times 1 constraints, and I wish to minimize the sum of x, being x these two semi-definite programming decision variables, well, we get successfully solved, and of course with exactly the same solution as linear programming. And well, this LMI set, I will explicitly write each of the 4 scalar inequalities as a separate LMI, and then I will call a plotting routine that I will discuss in a sequel video, because cosmetic plotting stuff is not the important thing at this moment. So if I plot the set of feasible values for those LMIs, then of course I get the polyhedra. And this orange dot is the so-called analytic center of the LMI, and it is the point that maximizes the product of the eigenvalues. All of them must be positive, so the point x in which the products of the eigenvalues is bigger is called the analytic center of this LMI. And well, my plotting software computes it, puts this orange circle. So good. The thing is that A polyhedron is, the simplest LMI set, but, well, we can think, for instance, in this LMI, in which this is a circle centered in the origin. If x is a decision variable, c will be the center, rho will be the radius, and this thing will end up being, for this particular case, this thing, and this matrix must be positive semi-definite. And if we compute the determinant, principal minors, then this must be positive, which of course is nothing. 1 is positive. The determinant of this thing means that x1 must be between plus minus 1, and the determinant of the whole matrix is the equation of the circle, so that if I plot the LMI set, I get a circle, and the analytic center is, the center of the circle. Of course, if I change my shape matrix, if I put a 4 here, then this is the new LMI that must be positive, and at the end I have the equations of an ellipse whose major axis is 2 in the horizontal direction. Indeed, if you know Schur formula or look for it elsewhere, if I have a matrix A, B transposed B, C, this thing is equivalent to A being semi-definite positive and A minus B transpose C, B, also positive semi-definite. So in this case, with this matrix, if I call this Q, then this being positive semi-definite means 1 minus x transposed Q minus 1 x being positive, and that's the equation of an ellipse with shape matrix Q. So the ellipse axes are oriented in the directions of the eigenvectors of Q, and the size is the square root of the eigenvalues. Details are not important here, but it's just that ellipses are a particular case of LMI sets. And then the next set we are going to draw is a kind of egg-like shape. This is the matrix that must be positive definite. And what is it? Well, we'll see in a minute. If we plot the set, we have the green egg with analytic center, the cyan circle, and it's kind of egg shape, in which, now we can interpret this as an ellipse which varies its shape, let's say, depending on the horizontal axis. So this non-linearly deformed ellipse is the egg. Or, if I take the determinants of this stuff, the minors, the principal minors are 1, which is nothing important. This thing is this quadratic constraint on x1, and the determinant of everything is this cubic constraint. When we plot the set that fulfills these 3 inequalities, well, actually 2, the first one is tautology, well, then we get this nice looking egg shape. The last examples we are going to put in this video are cones, in the sense that this standard quadratic cone, which is equivalently written is this? Well, you can check that indeed the minors of this matrix are x1 positive and x1 squared minus x2 squared positive. So this defines the cone, and if we plot it, well, this does not really exist. This extends forever, but my ad hoc plotting command, I did it in a simple way, so that rightmost extreme shouldn't be there, but okay. I was lazy to program it in a better way. So, well, this infinite cone is also an LMI set. And, well, if I change the LMIs and put whatever numbers I invented, this is another cone. And, well, I added second LMI, so I will plot the intersection of that cone and a very large circle, just because, my plotting routine got crazy if I didn't write this, but okay, this is not really part of the cone. This is just for the cone not to be infinite for my plotting. Then, if I plot the LMI set, I get this cone, whose axis is not horizontal, is this thing here, and whose apex, the vertex of the cone, is away from the origin. So we'll finish this video here, and we'll leave lifted LMI sets for the next video. In here we just define what an LMI set is. We checked that they were convex sets with polynomial boundaries, and the simplest sets were, the cones, like this, the polygons. We also could write circles and ellipses as LMI sets, and we can invent other egg shapes, or, if I invent a matrix of size 5 times 5, then I will have a set with a 5th degree polynomial boundary. So with this presentation about these non-lifted LMI sets, we conclude this video. Thanks for watching.